two different versions. As far as I understand, postdoc at the University of Texas, Austin, and previously at UCLA. And she's, of course, Italian, as you heard before. And she got a bachelor at the University of Trieste and then a master at Sorbonne University and EPFL. So we're very much looking forward to your talk. We're interested in your research activities, which spans abroad many ranges from condensed matter to open quantum systems. And let me just also mention that she also was recently awarded the NSF Career Award. That it's a very prestigious award in the US. So please, Benedetta, go ahead. Now we're not seeing the slides again.
Okay. Oh, now I can hear you again.
Yeah, but we cannot see the slides again.
Oh, yeah. Let me go back to that. Now, can you? Okay, let me see. I'm sorry, guys. Let me share the screen. Can you see the slides now?
Yes.
Okay. Sorry, I don't know if I lost connection, but I stopped hearing you. I guess you have completed the introduction.
Yes.
Okay. So, well, thanks a lot, and thanks a lot for inviting me. I think this might be the first time that, even if virtually, I give a talk in Italy. So today I'm going to talk mainly about one of our last projects, but I thought it would be nice if I gave you, a general introduction to non-Hermitian physics in magnetic systems, and also I will really specify what I mean when I say magnetic systems. And in this context, within my group, there have been many works. I will focus mainly on three, and I will really try to give you a different perspective, in the sense that I will show you how applying these non-Hermitian theories to magnetic system and generally spintronic setup is something that can really enable us to uncover novel dynamical phenomena and functionalities. And I will also show you how, at least from my perspective, magnetic systems with respect to other platforms have an advantage, in the sense that they have intrinsic non-linearities. And I will show you a specific example of how these intrinsic non-linearities can enable us to realize phases that are far from equilibrium and I think are very interesting. And this phase is a spin superfluid phase. So probably you're really familiar with the superfluidity or superconductivity that is sort of cousin of this phase. But I will just briefly guide you through what the spin superfluidity really means, and then I will show you exactly the type of system that we can realize, which is a dissipative driven spin superfluid, and it's really an instance of emergent non-reciprocity that does not rely actually on the skin effect and seems to have, properties that are related to, for example, black hole physics and also spontaneous entanglement generation. So let me start from the beginning and tell you just a bit about how I got interested in this field. So I've been working in spintronics for, I think, 10 years. So my PhD was focused on that. And there's been always a very functionality-driven approach to this field. And then I heard about these non-Hermitian theories, and I was very intrigued. This was, I think, 6 or 7 years ago. And I realized that, the key ingredients for non-Hermitian engineering at the end of the day are loss and gain. And loss is something that we have intrinsically in any magnetic system, both for the local loss and the non-local loss. And gain is something that we can achieve with very well-established experimental techniques. So I started thinking in these terms, and I started trying to apply these theories to magnetic systems. Now, what do I mean for magnetic systems? Since you can call a very boring heterostructure a magnetic system, and you can also talk about, for example, spin liquids. So I will discuss the, say, more boring magnetic systems, meaning the examples that I will make are mostly focused on these magnetic heterostructures that are really tabletop heterostructure that people build routinely. And here, what you do is to take a very thin ferromagnetic film, and then you sandwich it between metallic spacers. And it's very well known that this metallic spacer can mediate coherent interactions and also in some cases dissipative interactions. And this heterostructure can also be driven by spin torque and generally spin current injections. So I will take mostly this type of setup as an example of how you can substantially build metamaterials using magnetic system. But there are also magnetic systems that are more natural, naturally occurring, such as magnetic crystals, and those are not effective one-dimensional models. They are 2D and 3D, and in this case, you don't have to engineer the coherent and dissipative interaction. They just come naturally within the structure. So that's an advantage. On the other side, since these interactions are occurring naturally, it's also harder to tune them. However, some of these interactions are really interesting, and for example, people have been looking for decades at how one could potentially find topological magnonic phases that are due to some chiral interaction that, for example, emerge in van der Waals materials. So this was a topic that I was particularly interested in, I would say 7-8 years ago. And the interesting side of it is that most of the earlier proposals for example, realizing magnonic topological phases have relied on Hermitian model.
Sorry, Benedetta. Sorry if I interrupt you. I think there is some problem with your mic, which is making some noise. So it's not. I don't know if it was just me hearing that, but.
Let me see.
Yeah.
I can also hear it.
Yeah.
Okay, is it the same if I take the headphones off?
Try saying something.
Are you still?
Yeah, I still hear this kind of disturbance.
Oh, I am. Let me see what I can do. Maybe I can mute and remute myself. I'm not sure what it is because I had like a Zoom calls yesterday and everything was okay. So okay. If is it better just by restarting it?
Not really.
I'm not. Let me see. I'm sorry, guys. Microphone. Yeah, I'm not sure what that might be.
So you took the headphones off, or?
Yeah. Now I took them off. Is it better in any
No,
way?
it's like when. Not really. It's like when you speak, it's like hearing the sound of a fly, like when you have it in your ears.
So... Oh yeah, I know. I can imagine that is annoying. I have. Yeah, I'm so sorry. I have no idea what to do because I never had this issue.
Now it's off. Okay.
No, okay. Yeah, the only thing that comes to mind is maybe I should put this extra noise suppression, this beta.
Yes, it's better
Yeah,
now.
that it's Okay.
Yes.
Yeah,
Great.
okay.
Awesome. Now I don't hear you at all. I don't know the others.
Yeah, I can't hear you now.
Okay, now is it
Now, yes.
okay?
Yes.
Okay. I will
Yes.
keep everything as it is. Yeah,
Yes.
I'm
Sorry.
okay. No. Let me now reshare. To share screen. So okay, and is this okay? You can hear me. You can see the screen.
Yeah,
Yes.
perfect.
Yeah. Okay. Perfect. Okay. Okay. Let's hope the mic keeps working. Okay. So where I was, right? What I was mentioning is that a lot of proposals for topological magnonics have relied, at least for decades, on Hermitian models of the magnetization dynamics. And interestingly enough, at least from my perspective, there is not a clear-cut proof that topological magnons really exist. I mean, they most likely do, but it's really hard to use these Hermitian theories to predict a signal that can be measured and can be uniquely attributed to magnons. So one issue here is obviously the fact that all these models have been ignoring the presence of dissipation. But I think another issue here that is often not discussed is the fact that these excitations are bosonic, right? So you're dealing not with a nice electronic system in which you can just set a Fermi level and look at the transport due to your edge states. You're dealing with a bosonic system in which you thermally populate your bands, and it becomes really hard to understand whether, for example, a transverse signal is due to really edge states or just to some finite Berry curvature contribution that can be there even if the Chern number of your band is ultimately 0. So in this sense, we realize that adopting a non-Hermitian approach can solve in theory both problems. On one side, you're really not neglecting dissipation, you're not pretending it doesn't exist. You actually leverage its presence. And on the other, as I will show you in a second, adopting this approach can also circumvent this issue due to the bosonic nature of the system. So I'm not going to show you all the details also because if you are really familiar with these non-Hermitian models, you know very well what a non-Hermitian SSH model is. But I will show you more from a magnetic perspective what was our building block. And our building block is something that we call LLG equation, and it really describes the dynamics of the magnetization subjected to coherent fields, but also to its intrinsic dissipation that comes in this interesting form. This term is called Gilbert damping. It's phenomenological, but it actually works when you try to describe the long wavelength dissipative nature of magnetization dynamics. And then what you can also do is to inject some gain via spin injection. So this is really the building block. I would describe a single unit of this model. And then what you do next is to linearize the dynamics and derive an effective non-Hermitian Hamiltonian. So since we wanted to realize this SSH model, we thought about an array of coupled magnets. So it's exactly the type of heterostructure that I showed you before. And here, think about it as
Sorry, can I ask a question?
Yeah, absolutely.
About the Landau-Lifshitz-Gilbert equation that you showed before. So you are
Yeah.
considering this in its quantum version or in its semi-classical version? So for you, what is it?
For me, I would say if we are using the same semantics, I would say semi-classical, in the sense I'm going
So
to.
so you're assuming that you have an array of let's say of classical spins in your system.
Yes, exactly. So I'm going to use Austin-Primakov and
Okay.
rewrite this in terms of magnons, but I'm going to do it in the linearized version. So I'm dealing with large spins.
Okay. Okay, thank you.
Yeah, and right. So, and throughout this specific talk, I'm just going to deal with the large spins because what I'm trying to model, maybe let me also show you this. What I'm trying to model here with this magnetization vector is literally the spin of that describes the long wavelength dynamics of an entire ferromagnetic slab. So it's really a macro spin approximation. And so exactly. So when you think about this A and this B, you can think about this this ferromagnetic slab, and now through the by sandwiching them between some metallic spacer, I can engineer also coherent interactions among them. And when I linearize the system and I derive a Magnon Hamiltonian in a periodic quadratic limit, what I see is that my edge state, which I can find if I tune the system to a PT symmetric point, my edge states are going to have a finite imaginary energy, and they come in complex conjugate pair. So what we liked about this is the fact that now, even if the system overall is dissipative, it has an edge state that has a lasing type of behavior. So this is very well known, and it's the standard non-Hermitian SSH model. I think really the step that we took further was then to identify the regime of parameters for which we can create this model and simulate the nonlinear magnetization dynamics. So we just went back and simulated the coupled LG equations that described a system of I think 10 coupled magnets, and it was not obvious a priori whether the presence of this topology requires fine-tuning and is just survives at the linear level. And what we found is that even when the all the nonlinearities of the magnetization kick in, you still observe a very clear topological signature. And when I'm showing you this plot, I'm plotting the microwave power that is emitted by each element of this array. And you see that for a very long time, even if you are injecting every A site and you're driving it far from equilibrium and also far from the linear regime, the only lasing that you see, it's the one correspondent to the site that displays the topological edge mode at the linear level. So this was really our first attempt in trying to...
Sorry, Benedetta, can I ask you a question?
Yeah, of course.
So what does dictate this critical time when this happens, or like this spike we see?
Yeah, that's a really good question. We did not. It's not. So I don't have really a crisp answer for you because to answer this, so we just, and I will show you in a while in different contexts, we just started looking now at, not only at simulating the nonlinear magnetization dynamics of this couple heterostructures, but also trying to understand them. And it's quite complex mathematically. So, yeah, unfortunately, I cannot give you a sharp answer. I would, I could think about it. I would say that it's something that it will depend on a lot of parameters, in the sense that if my J1, right, is ferromagnetic, which was the case in our model, now, for example, and I'm simulating, this one is driven, this one is not, the other one is driven, and really is actually driven very far from equilibrium, you know, there would be, the J1 is going to try to keep them aligned, so it's going to fight against the spin misaligning and starting lasing. Obviously, there is also the influence of Gilbert damping, which is going to try to realign the spin by means of dissipation. And then there is the strength of the current that you're applying. So you see there are a lot of parameters that enter in what really then determines the exact time. Right, so, but in any case, this was really our first, trial. We really tried to understand whether applying this type of theories would lead us to observe something that is really already there at the level of the LLG dynamics. But if you don't have this non-emission perspective, you can actually not see it. You will never find, if not by luck, these regional parameters in which this type of effects happen. So then we look at several other phenomena, such as exceptional points. But just for the sake of brevity, and because we don't have infinite time, let me focus on a specific one. So what we ask ourselves is whether this non-emission skin effect, which I imagine you're familiar with, so this really breakdown of the bulk edge correspondence at the level of just the non-emission Hamiltonian is present in magnetic systems. And when we ask ourselves this question, really first issue that we have is the fact that if you want to claim that a skin effect is there or not, you have to be able to compare your periodic boundary condition spectrum with the open boundary condition spectrum. And to derive an open boundary condition spectrum, I need a lattice model. So the question really became, how do I describe dissipation in a lattice model for a magnetic system? And we couldn't find any work that did that. And I don't think it's a coincidence, simply because it's an extremely complex problem to tackle microscopically. And I think a PhD student could lose 2 years of focusing on a specific material and all the possible mechanisms that will eventually dissipate angular momentum. So we really took a very different approach, and we just said, okay, let's consider this 2D van der Waals magnet. Now, I know exactly how to write the coherent part of the Hamiltonian. So let me just make a phenomenological ansatz for the dissipative part that capture both local and non-local contributions, so both k-dependent and independent terms. And it's also consistent with the, for example, the crystalline symmetries of the system. So we did that, and we try also to match the k-dependent part of the dissipation to some ab initio results that we found. And ultimately, the main takeaway from this is that we realized that no matter what you would add to this phenomenological model, or no matter the actual value of these phenomenological parameters, the real key ingredients to realize the skin effect were the simultaneous presence of DMI-like interactions, so this coherent emission but chiral type of spin interactions, together with non-local dissipation. And if you switch off one or another, things don't work anymore, and you lose the non-emission skin effect. So this was, I think, 4 years ago or 3 years ago, and honestly, at the beginning, we really couldn't understand why. So we tried to run a lot of symmetry tests. We know that at the level of the magnetic Hamiltonian, when you have DMI, you lose time reversal symmetry. But still, we couldn't understand why we needed both. And also another question that we asked ourselves is, okay, admitting that there is a skin effect, what do I tell an experimental colleague? What can this colleague really measure? And to really try to answer these questions, we adopted a much more controlled approach. So we moved away from this 2D crystalline structure, and instead we thought, okay, let's go back to this simple magnetic heterostructure. It's effectively a 1D system. We derived also, because of some other interest that we had, we derived a full master equation approach that connects the dynamics of the spin to the response function of a reservoir and its symmetry properties. But to make a long story short, what this project gave us in terms of insights was something that a posteriori is quite obvious, but I think was a bit hidden, at least from my perspective, in all these very formal, abstract non-Hermitian theories, which is you can have an Hamiltonian. This Hamiltonian can display a non-Hermitian skinny effect. You can have a finite winding number, but at the end of the day, that's not enough to tell you that to answer the following question. If I inject some spin in the middle of the chain, will I see some non-reciprocal accumulation? So to answer that question, you have also to account for local dissipation. So, K independent terms, and you also have to account for macroscopic details such as the length of the system. So while you can observe this Magnum accumulation, actually depends not only by the presence of DMI and local dissipation, but also on all the details of your experiment. More interesting, what we realized finally by rewriting our problem in a simpler form was, why do we need to have DMI and non-local dissipation at the same time? And we realized also that, and we were not familiar with these works at the time, we realized that this is actually something quite well known in the context of reservoir engineering of open quantum system, and it was proposed by Clark and Anja Mettelman in 2015. So you can see it clearly here. I'm writing the interaction between just two spins in my model. Now you have a term like DMI, right? And this term, because of the chiral nature of this interaction, comes with an imaginary unit, but it still has to be Hermitian, so it has to switch sign when you look at the two off-diagonal components. On the other side, you have also non-local dissipation, and now you can, I think, easily see that by tuning the relative ratio between D and gamma, you can really imprint effective non-reciprocity in the system. And what is really the condition here? But first of all, you have to break hermeticity, right? That's why you need the non-local dissipation. And then secondly, you need a phase that you cannot gauge out. And you can prove rigorously that this is related to having time reversal symmetry breaking coherent interactions. So interestingly, these interactions are quite ubiquitous in magnetic systems. So in theory, the skin effect is there. However, getting back to the previous point, it's not obvious whether you should observe it or not, because microscopic details matter as well. So then we looked again a few years later at the same type of setup, and together with Lorenza Viola and my new postdoc, Vincent, who was our PhD student, we started asking the question of whether we can use these platforms to investigate some of the phenomena that they were interested in, which I will explain in a second. And especially, can we investigate, for example, metastability or topological lasing in these systems? And focus on the robustness of this phenomena with respect to nonlinearities. So everything that I told you in the context of the skin effect was done in the so-called linear regime. So there was no drive, right? I was just considering a system in which there is some dissipation. So even if the magnetization, because of thermal fluctuation, goes away from equilibrium, it will do so in very mildly. So now instead we are interested in looking again at the same system, but we are going to drive this system, each magnetic layer, far from equilibrium, and by doing so, we will really have an opportunity to experience how nonlinearities play a role. And so this is really the term that I also showed you before that is going to push us away from equilibrium. So we started working together on this. We took the magnetic heterostructure that we studied in the context of the skin effect, and we started driving it far away from equilibrium. We found a lot of things that hopefully will soon be on archive, but I don't have really the time to go through all these phases. So I will focus on this phase, which we called... do you have a question? No. I will focus on this phase, which we call spin superfluid limit cycle. And here the key is that if you have a system that is intrinsically nonlinear, you can truly access dynamical phases that you will never be able to realize in a linear dissipative driven system. And from a dynamical point of view, a limit cycle is exactly that. So this limit cycle realizes a spin superfluid state. So I thought that many people might not be familiar with that. So I just want to give you a feeling of what spin superfluidity is, and this is a concept that was introduced at equilibrium, and it's called spin superfluidity because it's really the spin analog of superconductivity or superfluidity as the one that you find in helium. And this was realized in this very beautiful paper by Alperin and Onenberg already before, at the end of the 60s. So what they noticed is that when you write down the magnetodynamics of certain systems, such as easy plane ferromagnets, that dynamics maps very closely to the very well-known superfluid hydrodynamics. So a way to understand this is just by staring at this Hamiltonian. Here we are describing an easy plane ferromagnet. So there is a magnetic field that wants my system to be aligned along the z direction. And now, because of the easy plane, the magnetization will tilt, right? And when it tilts, it has to tilt at a certain angle phi. But the energy does not depend on that angle, and this is obviously symptomatic of the fact that you have one symmetry in the system and you're spontaneously breaking it by your ground state. So you will have an emergent Goldstone mode, and that's exactly the spin superfluid. Now, turns out that this spin superfluid state that people have been searching for a while is not, first of all, as perfect as superconducting currents or through helium superfluidity, in the sense that there is always in a magnetic system some weak U1 symmetry breaking mechanism that will make your spin superfluid transport experience dissipation. However, it's still a very intriguing state itself, because if you look at spin as carried by thermal magnons, this type of currents are just going to decay exponentially. And instead, when you assume that there is a spin superfluid there that you actually access as a metastable state, because you have to fight these parasitic effects, this state should carry your angular momentum much more efficiently. So there have been some debates on whether this state exists or not, and there's actually some claims that are not very believed in our community, that it was found in some easy plane antiferromagnetic system. And soon we are going with some experimentalists to have a paper out in which we claim that is instead present in another system. But this easy plane ferromagnets and antiferromagnets are just the most canonical example of spin superfluidity. If you go back to some Russian literature of the 70s and 80s that we had to do, you find out that there has been also another candidate for spin superfluidity, and this is an helical magnet. Now, if you notice at the level of coherent interaction, I am having exchange, a magnetic field, and a nearest neighbor DMI. So I'm writing down the coarse-grained limit of the systems that I've been introducing you to in the context of our work on the non-Hermitian skin effect. Now, if you look at this free energy, I mean, at least the first time I realized this connection, I was like, well, but why this is a spin superfluid? So something that, I mean, this for me was nice to notice is that if you perform this gauge transformation, so you define now this covariant derivative, which is a sort of, now you, instead of being like a linearly propagating spin wave, you are, a spin wave that propagates with a built-in twist. So as you propagate through this spiral ground state, you experience the texture as an effective easy plane anisotropy. And then you have a one-on-one mapping with the models that I showed you before. So that's where the mapping comes from. But again, similarly to is more well-known easy plane analog, this state was proposed as a spin superfluid state, but it was never experimentally detected. And I think one of the big issues here is that it's very hard to tune the system to the strength of the MI that you need in order to have this state. Not only because this type of very strong DMIs don't emerge in crystals, but even when you are engineering these heterostructures and these interfaces, it's very tough for the experimentalists to even crank up DMI a little bit. So what we found instead, by driving our magnetic heterostructure out of equilibrium, is that by a complex interplay of gain, loss, and nonlinearities, you can stabilize this chiral spin superfluid state as a limit cycle solution. And that we are driving the system, and eventually the system enters in this spiral. And I will show you soon a picture that hopefully explains a bit better. And it really stabilizes this spiral as a limit cycle solution. Now, how often can you stabilize limit cycle solutions in magnetic system, magnetic heterostructures in a lab? So the answer is actually you can do it fairly simply. And I'm just showing, for example, this is an actual experiment, and they show that they can build these arrays, like 20 spinol actually 50 spinol nano oscillators, and they can do it with such a precision that they can synchronize them. Or there's been a lot of work done recently in the context of creating neuromorphic networks using these magnetic elements that I'm describing here. So limit cycle solutions happen, and we're pretty confident that it can happen. It simply was, it was never, people never tried to realize it for the in this to satisfy this specific model. Now, how does this look? So what is happening here is that we have this, say, 10, 20, as many as you want, maybe 50 layers, and these layers are experiencing some local loss, gain, and some coherent interaction, including DMI. Now, we are driving them strongly out of equilibrium, and ultimately, they reach this limit cycle solution. So there is an attractor dynamically, and they enter in this limit cycle solution in which you have the spiral that I showed you before in the equilibrium case, right? So this every spin here is a magnetic element, and they're all realizing this spiral state, but they are not static. They are processing at a certain frequency. Now, this frequency is just the system picks the frequency. So here, I think that's maybe important to underline. Here we are driving the system out of equilibrium, but we are doing this with a DC drive. So we are not picking a system. The system itself is a spontaneously breaking time reversal symmetry. And I'm writing here time crystal, but I'm not making a claim that this is really a time crystal in phases, but it's still a phase that spontaneously break U1 translational symmetry in space and translational symmetry in time. And the question that we asked ourselves after we finally understood this dynamical phase was, okay, how do magnons propagate along this time-dependent spin texture, this spiral with a pitch determined by K and a uniform precession frequency. So I really have to credit Vincent to do all this math heavy lifting. It's very, you cannot answer this question in the laboratory frame of reference. It's just really messy. So what you have to do is to perform a series of transformations that enable you to be in a frame of reference in which, your system is just a static unbound ferromagnetic polarized phase, and then it's very easy to define also empirical transformation with respect to that. So the first step, which is simple, is to perform a rotation in time. So we go from here to a frame of reference in which the spiral is not precessing anymore. What is mathematically more annoying is to perform this transformation in space such that now I'm unwinding the spiral, right? So now the spins are aligned. And then finally, last but not least, we take the spins and we realign them with respect to the North Pole. So after you have done all that, you have an effective dynamical equation for the fields, and these fields are really the creation of a magnon along the direction of the magnetization in this superfluid frame of reference, or the annihilation of the magnons. Here we need to, since now this state is breaking U1 symmetry, right, explicitly, now we really need to call these two fields particles and holes, and it's just more convenient to think about them as particle and node that create or annihilate, that create an excitation that is H bar or an excitation that is minus H bar. So this is our equation, our dynamical equation. And if you ignore for a second Gilbert damping, you can think about GQ as the Hamiltonian, the BDG Hamiltonian that is describing the excitations about this superfluid limit cycle state. So here, what I'm saying is that particle hole is meaningful. I mean, it's always meaningful, but what I've been used to see dealing with magnetic system is a particle hole that is introduced just because it's a particle hole that doesn't really mean something, in which your negative energy excitations are just a mathematical construct that allows you to diagonalize your matrix. Here instead the whole excitations are meaningful because they have a finite frequency in the laboratory frame of reference. And
sorry, Benedetta, can I ask you a question?
Yeah, absolutely.
Is this alpha the same one that was in front of the damping term?
Yeah, this is Gilbert damping.
Okay.
Yeah, and maybe one thing to notice that I didn't mention is, so we started with the Gilbert damping and with the drive. And interestingly, after you perform this transformation, what you get is effectively a pseudo-emission system, because here the drive enters only in coherent parameters. It's not doesn't look anymore like a non-Hermitian parameter. So the drive obviously enters in our Hamiltonian, but you see, just in terms of determining the coherent frequency of our state, it's a non-Hermitian component gets absorbed by this transformation. So here we have we have a pseudo-Hermitian dynamics in which there is just some boring damping that is diagonal. And
what about the gain part? Is it included somewhere in the equation?
The gain, right? Because you would imagine, indeed, what you would imagine is that now, for example, you have another term that is like a plus imaginary unit gain. It doesn't happen. It just the gain is inside here. but is inside, it enters only in determining coherent parameters.
Okay.
See, like the frequency, the coherent frequency, for example, will depend on the gain, but it's an Hermitian term.
I see.
Yeah. So yeah, exactly. So the gain really disappear, and paradoxically, in the limit of very small dissipation, through this interplay of gain loss and strong nonlinearities, you kind of land into a coherent state, and that's this limit cycle. And now this coherent state, or this limit cycle, what's happening is that we started with the magnetizational line along Z, and now we are pumping a lot the system, and we are entering this limit cycle state that breaks explicitly U1 symmetry, right? It's not anymore aligned along Z. So this means that you have this BDG form in which particle and all like excitations are coupled. And now we realize there is a direct mapping with the U1 broken condensates. So you have this anomalous pairing between a magnum fluctuation at wave vector Q and its time reversed partner. So in the context of magnetic systems, the presence of this pairing translates into squeezing. For example, antiferromagnetic system have a naturally squeezed ground state, and here we find the same squeezing, but now this squeezing it's parametrical. And if you're interested, I can tell you more along that line. But it's really this superfluid limit cycle is, from the point of view of the magnon, excitation on top of it acts as a parametric pump that is creating this particle-hole pairs. Now we have our effective pseudo-Hermitian Hamiltonian, so we can diagonalize the system, and what we find is that our particle-like excitations have speeds that are asymmetric. So now there is a non-reciprocal propagation, and it's very important to notice that here we tune the non-local dissipation to 0. So there is no Hermitian skin effect. This non-reciprocity really stems from something different, and I think of it as a really flow-born, in the sense that what really happened there is that this limit cycle solution, so this superfluid background, has broken Galilean invariance. And that's why the magnons on top of it, so I'm showing you here some more concrete example, the magnons on top of it propagate in a non-reciprocal way. So, okay, this is the limit cycle region of stability that I've shown you before. And this is the pitch of a spiral solution. So here what we are doing is to say, okay, we keep the pitch fixed, but what you can do very easily in the lab is to crank the spin current injection. So you can go now from regions that in which your solutions are only unidirectional. These are the right particles, and these are the holes. And as you can see, this dispersion is telling you that you can just propagate, towards the right, and you cannot propagate towards the left. And then, as you go here, you can actually find even regimes that are perfectly bidirectional, or almost. Right, as this is an example. And then if you crank your current even more, you can access the opposite regime, right, in which I haven't plotted here, but actually this is an example in which your excitation can just propagate towards the left. So there is no reciprocity that has nothing to do with the non-Hermitian skin effect. And I don't know if maybe how familiar all of you are with these concepts. I was not at all 3 months ago when we started finding out about this. These are the points in the points at which the velocity of your excitation go to zero are technically horizons, our momentum space horizon. So what it means is that if you, let's say, if you actually launch a spin wave that matches that wave vector in momentum space at which the velocity becomes zero, it will just get stuck, like frozen. But I will show you in a second a more physically intuitive example of the generation of these horizons. But here's something else that is also very interesting, and actually realized just in the last few weeks, ties together all the story, is that if you look at the anomalous correlator part, you will see that there is a lot of squeezing. And actually, this squeezing is more intense when you are in the unidirectional regime rather than this bidirectional regions. And this is really signaling the presence of pairs of particles and Hall-like excitation. And
Sorry,
this
Benedetta,
yeah.
When you say that it has nothing to do with the non-Hermitian skin effect, you mean in the sense that the hoppings are not different, but still you have these two velocities which are different, right?
Yeah.
And this doesn't imply some accumulation of magnons at the boundaries, or?
Well, so that, I mean, in the sense there will be no reciprocity, right? So, so if I have a finite size system and I start injecting, and the system is non-reciprocal, yeah, eventually I will see some accumulation. But when I say, but this accumulation that is just the result of non-reciprocity has nothing to do with the non-Hermitian skin effect, in the sense that if I look at this Hamiltonian, it's actually pseudo-Hermitian.
Okay.
So if I, let me try to set it in a different way. If I took this G, that is pseudo-Hermitian, and now I diagonalize it, open boundary condition, periodic boundary condition, there is no, nothing special happens.
Okay.
Yeah, so there is definitely no reciprocity, but it's really, it's emergent. It's because you fall into this background that breaks Galilean invariance. And maybe something that could make it more clear is that now we are looking at the magnon excitation on top of this superfluid spiral that moves at this constant, that precesses at this constant frequency. This state carries a finite amount of spin superfluid current. So now, from an hydrodynamical point of view, what we're doing is to look at excitation that propagate on top of a background that has a net flow. Maybe that can explain it in a from a different perspective. Maybe one last thing that I will show you is the following. So as I was mentioning here, we realized that as we change the current, we can access regions that in which our excitations have a very different type of mobility. So we thought, okay, what if we have this long magnetic heterostructure, and in one region the current will be set to a certain value, but in the other region we change the current such that we have a unidirectional dispersion. So what if we create a scattering geometry in which we have a region A in which my excitation can propagate in both directions. Then I have a region B that is almost unidirectional. I mean, if you just focus on the long wavelength physics, it's really unidirectional. And if you look at higher K, and that's actually the key of why we see this reproduction, you have a state that can propagate. But at the level of long wavelength dynamics, this is absolutely unidirectional. So this is the region B, and then I just have another region A. So what do we see? So what we are doing here, what I'm showing you, is a simulation in which we start with a Gaussian wave packet in our region A that contains states of this type and states of this type. Hopefully you can see my cursor. Okay, so we launch this wave packet in region A, and you will see there are two components, right? One that moves to the left, and one that moves to the right. So the one that moves to the left is not really what we are interested in now. So what we're interested in is what happens to the one that moves to the right. So now these particles are coming on this interface. Okay, so the key here is that these are A and B are two different systems. So the eigenmodes of A are not the eigenmodes of B. Now these particles want to tunnel into B, but you see they cannot really do it by keeping their momentum fixed, because the velocity is flat, so they are really like hitting an horizon, and they get pushed back. So most of it will get reflected. However, there is a small part of this wave packet that manages to tunnel through the higher momenta states. And when you do this, since these are not the same eigenstates, you will see, it really comes from, like you see it in the math, that the only way in which this can happen is by means of pair production in the B region. So here, what happens in B is that you start generating a lot of pairs of particle and all pairs at this higher momentum, and this is very, from a condensed matter perspective. So the analogy is not one-on-one, but it's very similar to the process of Hawking-like emission, and then some of these can even tunnel in the next region. So right, and this really hopefully we will have it. Actually, we will send it tomorrow to archive, but we are still kind of trying to tie all the story together, and I think there is a lot to do. So since I'm going over time, I'm just leaving you with the conclusion and the outlook, and yeah, thanks a lot for the invitation and for your attention.
Thank you. I don't know if there is a button to clap here, but
I don't know, don't worry.
okay. So are there any questions? I have maybe another one. We had some during the talk. So you consider just one-dimensional chains because of this experimental platform you have in mind, I guess. So
Yeah.
Because at some point you said that in order to have this non-reciprocity, you need non-local dissipation and chirality, with which I agree. But I know that if you have like quasi 1D structure, like I don't know, an array of plaquettes, there you can have this non-reciprocity even just with some chirality, maybe some artificial flux, and just local dissipation. So I was wondering if you can also engineer quasi 1D systems instead of just purely 1D.
So I guess, okay, maybe just starting from the beginning of your question. So when I'm talking about this project, right, so this non-reciprocity due to the non-emission skin effect, it's, I'm, here I need, it just happens naturally. There is no local dissipation that this metallic space are mediated because of the spin pumping, and so I need non-local dissipation. I need chirality. When I move to the non-linear regime, I don't need non-local dissipation anymore. I just need the chirality and local dissipation. So probably very similar to what you're describing. Right, so these are is the same structure, but even if the non-local dissipation in this last example is practically negligible, I will still get a non-reciprocity. I'm not. Though I'm curious about this. Maybe you can send me this paper, like the plaquette that you are mentioning, because right, because what I'm familiar with from this more non-emission perspective is this approach of discovered by Clark, in which you balance the chiral with the non-local. So I would be curious to see how the
Okay. So if there are no more questions, we can thank our speaker. Again, thank you, Benedetta, for